Welcome to Modeling Groundwater Chemistry with FreakC, FAST, and Python. I'm Walt McNabb, a hydrogeologist and computational environmental scientist. I work as a consultant in the San Francisco Bay Area in California. In this lecture, we're going to briefly step through some organizational items for the course, and then move on to an introduction to geochemical modeling. The objective of this course is to teach you how to set up and run FreakC simulations, and later, how to extend this knowledge to running reactive transport models with FAST. The emphasis is on practical issues, what different features in FreakC are for, what types of assumptions are appropriate for what types of problems, and understanding the contents of the input and the output files. There's much less of an emphasis on the theoretical model underpinnings, although you're certainly welcome to pursue that on your own and ask questions. There will, however, be some introductory theoretical overview material in the beginning, so you have an idea as to the concepts that go into the model. As for the course itself, the videos and course notes are intended to provide context for the example problems, instructions on how to set up the problems in FreakC or FAST, and discussion of the model output as to whether or not it's reasonable. There are a few questions and exercises for you to think about. However, much of your learning will take place on your own by downloading the input files and running them both with and without modification to see how the models work. At the end of the course, we'll also tap into Python and see how scripting can be used to enhance our capabilities with these models. So the course is organized into modules. The first contains some introductory material, and then we will move on in subsequent posts to work directly with FreakC. We'll start off with basic concepts, such as equilibrating a solution with a mineral phase versus adding a reactant, and then gradually move on to more complicated concepts, starting with solid solutions and gases, and then on to redox reactions, reactive mineral surfaces, and chemical kinetics. Later, with a foundation with FreakC out of the way, we'll introduce chemical transport into the mix, so to speak, using the U.S. Geological Survey's FAST model. FAST uses FreakC as its geochemical simulation engine, so the two fit together rather nicely as part of the same course. So with all that out of the way, let's get started. Module 1 is an introduction to geochemical modeling. Here we will define what a geochemical model is. We'll provide an overview of the key concepts and equations and get an idea as to what kinds of computational issues need to be resolved to build a quantitative tool to assist. So a model is a limited mathematical representation of a system. For a geochemical model, this includes relationships between dissolved components in the aqueous phase, perhaps in contact with a mineral assemblage or even a gas mixture. In almost any case, the model will make idealizing assumptions, let's say an assumption of instantaneous chemical equilibrium, and neglect other processes such as microbiological controls on chemical reaction kinetics. Having to make idealizing assumptions is a requirement to keep the problem tractable, and oftentimes the response to having limited data, or for that matter, limited time and budget within which to complete a project. For those of you who are groundwater modelers and used to thinking about flow and transport in 1, 2, or even 3 dimensions, keep in mind that a geochemical model by itself is usually a zero-dimensional one, sort of like a well-stirred laboratory beaker. As soon as we introduce transport into the problem definition, we're talking about a reactive transport simulation in that case, which is a topic we'll touch on in later modules. So there's a pretty large variety of applications one can think of for geochemical models. These would include, for example, predicting the mobility of trace metals in contaminated groundwater, designing remediation systems, acid mine drainage, looking at the formation of ore deposits, looking at soil formation, looking at processes in playa lake environments, looking at weathering of concrete, both above ground and below ground, subsurface CO2 storage, and many other topics, some of which we'll be touching on in later modules in this course. So at this point, it's important to distinguish between a forward geochemical model and an inverse model, because FreakC does both. A forward model attempts to predict changes in water chemistry once equilibrium has been disturbed somehow. This disturbance could include bringing the solution into contact with a mineral phase or a gas mixture that it previously wasn't contacting before, or by mixing the solution with a volume of a different water composition altogether. Essentially, the geochemical model uses thermodynamic considerations to generate these predictions. In contrast, an inverse geochemical model attempts to constrain the extent of mass transfer reactions or mixing between different water compositions that could explain how one water composition is turned into another. In this case, the model uses mass balance considerations to constrain a set of possible mass transfer reactions and mixing proportions to arrive at an answer. This is a fundamentally different focus and mindset than the forward model. I'm mentioning this here because we'll be working exclusively with forward models in this course. Inverse modeling is a topic all on its own, in my view, and comes with many added complexities and idiosyncrasies. It's an advanced topic and something to look into later once Freak-C itself has been mastered. So let's consider an aqueous system in equilibrium with calcium carbonate or calcite. There's a mixture of ions and complexes in solution at any given time, and the makeup of the system is subject to change. For example, if you look at the carbonate complexes we might find, and these would include carbonate, bicarbonate, and undissociated carbonic acid, you will note that they differ from one another based on the number of attached protons, H plus ions, essentially. So in a very acidic system, there will be many more protons available, and the system will shift towards having more of its most protonated form present, undissociated carbonic acid. You can think of this system in a state of dynamic equilibrium, with complexes continuously breaking apart and forming again, and the relative proportions described with sets of equations. So what are these equations? Let's consider a simple aqueous system with no mineral or gas phases present, at least to start. First, mass balance must exist for each element in the system at all times. This seems obvious. Mass shouldn't be miraculously created or destroyed. In this case, mass balance must be maintained for calcium and for inorganic carbon, for example. The same can be said for the next constraint, which is a charge balance constraint. Here, the balance equation is weighted by the electrical charge of each of the individual species, as we've shown here. Calcium ion, for example, has a charge of +2, so that's weighted 2 times in the charge balance equation, for example. Next, note that the law of mass action states that the ratio between the concentration of reactants and products in a chemical reaction at equilibrium is constant. Here are some of the reactions that we would expect for our example system in the aqueous phase, with the data taken directly from one of Freak-C's databases. More on that in a later module. This leads to a mathematically well-constrained way of organizing the equations, with a total of 8 unknowns and 8 equations for our example system. There are 2 mass balance equations for calcium and inorganic carbon, which are used to determine the concentrations of the respective master species, in this case, calcium ion and carbonate. There are 5 mass action equations for the secondary species, including hydroxide. And there is a charge balance equation for the proton concentration, or pH. The proton could also be considered a master species. And remember that pH is approximately the negative logarithm of the proton concentration. With these equations all in mind, it is possible to build a spreadsheet model to iteratively solve the mass balance, mass action, and charge balance equations simultaneously for a simple system. The spreadsheet cells on the left on this particular graphic solve all of the equations as indicated except for the charge balance, with each iteration using estimates from the prior iteration to improve the result. The spreadsheet cells on the right use the same iterative model, but also uses the solver function in Excel to arrive at a pH estimate, which minimizes the charge balance error at the same time. You can download the carbonate equilibrium spreadsheet from the class materials and try this out yourself. So here are comparisons of predicted concentrations generated with our simple spreadsheet model against the results of the same problem run through Freak-C. More on how to do this in the next lecture. The results on the left, using smaller total concentrations of calcium and inorganic carbon, agree pretty well. Those on the right, with higher concentrations, begin to deviate a bit, though. Why is this? Well, one part of the explanation could be that at higher pH values, there are some other species that come into play that are not considered by the spreadsheet model, but are considered by Freak-C. However, there is another important issue that's coming in play here. That issue is the concept of thermodynamic activity. Up until now, we've used the species concentrations in the mass action equations. This is really only theoretically valid at very low concentrations. At higher concentrations, non-ideal effects become important. These include interactions between ions in solution, between ions and the surrounding water molecules. To deal with this, we introduce the concept of thermodynamic activity, which involves a correction term to the concentration. It is the activity of a species, rather than its concentration, that must be used in the mass action equations. So why am I bringing this issue up? Because geochemical models must include a means for estimating activities. An example of a textbook approach is shown here. This is a Davies equation, which posits a relationship between the activity coefficient for a given species, its electric charge, and the ionic strength of the overall solution, as defined here. At very high concentrations, such as in brines, interactions between ions become ever more complex, and simple expressions like the Davies equation may no longer suffice. Specialized approaches are then warranted, a topic we'll touch upon a little later. So after all of this, there are still more equations to add as we generalize the systems we'll be looking at beyond a simple carbonate equilibrium in a beaker. These include mass exchange reactions between the aqueous phase and amineral phase or mineral phases, mass exchange reactions between the aqueous phase and a gas phase or a mixture of gases, oxidation reduction reactions that involve electron transfer, surface reactions, reaction kinetics, solid solutions, etc. All of these considerations require their own sets of simultaneous, generally nonlinear equations to solve. So you can see where this is going. A full numerical model beyond what you could put together with a spreadsheet is going to be warranted most of the time. As a final set of thoughts, before we move on to Freak-C itself, always keep in mind the following practical questions when deciding to actually use a numerical geochemical model, now that you know what sort of goes on behind the scenes with one of them. First of all, can the system be modeled assuming equilibrium conditions, or must reaction kinetics be considered? More on how to do this later in Freak-C. Are all of the important species and phases for your problem represented in the model's database? Are the thermodynamic constants in the database accurate? For some trace metals in some systems, this may not be obvious. For the actual problem, how good are your actual data? Are all the species represented? Are the measurements accurate? Aluminum and iron data are notoriously problematic, for example, and tend to be reflect overestimates as a result of suspended material and so forth. Do you understand the oxidation reduction conditions in the system? This is a special problem as well.